This video introduces us to one of the most important concepts in chemistry, the mole. The mole is the SI unit for quantifying the amount of matter, and it is used as the chemist counting unit. By now, we know quite a few things about atoms, molecules, and ions. For example, we know that atoms are very, very small, of the order of picometers, and atomic nuclei even smaller, of the order of femtometers. We know that the masses of atoms are also very, very small, of the order of 10 to the minus 27 kilograms for the hydrogen atom and up to 10 to the minus 25 kilograms for the uranium atom. And we also know that their numbers are huge. Even very small samples of matter, for example, a teaspoon of water, contain billions of trillions of molecules of water. And a cube of sugar contains a similar order of molecules of sucrose. These numbers are just way too large to deal with in everyday counting, but we do need a way of counting them. We do need a way for accounting for the very large numbers of atoms, molecules, and ions that we see in everyday samples of matter. And that's because chemistry and chemical equations basically involve counting amounts. For example, here's a chemical equation for the combustion of methane, and it is a quantitative expression that one molecule of methane reacts with two molecules of oxygen to produce one molecule of carbon dioxide and two molecules of water. The problem is, even the smallest chemical samples contain huge numbers of atoms, molecules, or ions, and we are never going to start with one or two molecules, or even with a few molecules. We are typically going to start with trillions upon trillions of molecules. So to deal with such large numbers of atoms, molecules, and ions, we introduce the SI unit for amount, called the mole. Now, the technical definition of the mole is the amount of matter that contains as many objects as the number of atoms in exactly 12 grams of carbon-12. And it's not a coincidence that the definition of the mole is linked to the carbon-12 isotope, in the same way that our definition of atomic mass units was also linked to the carbon-12 isotope. And we will see in subsequent videos how that link arises. For now, however, the number of carbon-12 atoms in 12 grams of carbon-12 is approximately equal to 6.022 by 10 to the 23. So 1 mole can be said to be equivalent to 6.022 by 10 to the 23 objects. So for example, 1 mole of carbon-12 would be equivalent to 6.022 by 10 to the 23 atoms of carbon-12. 1 mole of oranges would be equivalent to 6.022 by 10 to the 23 oranges. 1 mole of paper clips would be equivalent to 6.022 by 10 to the 23 paper clips. And 1 mole of water would be equivalent to 6.022 by 10 to the 23 molecules of water. Now, the mole is simply a counting unit, and students of chemistry often get confused simply because the mole represents such a large number. But you are already very familiar with the concept of counting units. For example, you know the counting unit of a pair. You know that 1 pair of anything, for example 1 pair of shoes, is equivalent to 2 shoes. You also know that 1 dozen eggs is equivalent to 12 eggs. And you may know that 1 gross of pens is equivalent to 144 pens, and 1 ream of paper is equivalent to 500 sheets of paper. All of these are convenient counting units that we use to help us quantify large or relatively large numbers of objects. In chemistry, we use the mole to quantify large numbers of objects such as atoms, molecules, or ions, and so 1 mole of water would be equivalent to 6.022 by 10 to the 23 molecules of water, given that water is a molecular compound. The mole is the SI unit for amount, and as I've said, it's a counting unit. These other counting units are also valid counting units, but they just don't happen to be the standard recognized SI unit for quantifying the amount of objects in a sample. The number 6.022 by 10 to the 23 is such an important number in chemistry, it's given its own name. It's called Avogadro's number, and it's named after Amedeo Avogadro, who was important in developing the concepts of quantifying the amounts of atoms, molecules, and ions. Avogadro's number also has its own symbol, Na, and as students of chemistry, we really need to commit this number to memory to 4 significant figures, 6.022 times 10 to the 23. Given that 1 mole of objects is equivalent to 6.022 by 10 to the 23 objects, then it follows that 2 moles of objects would be equivalent to twice that number, 2 times 6.022 by 10 to the 23, which equals 1.204 by 10 to the 22. Half a mole would be equivalent to a half, or 0.5 times Avogadro's number, or 1/2 of 6.022 by 10 to the 23, which equals 3.011 by 10 to the 23, and so on. And if we had any number of moles, for example, X number of moles, then the number of objects, or the number of atoms, molecules, or ions in a sample, would be X times Avogadro's number. Now, this concept is very important because there are many occasions where we actually want to be able to interconvert between the number of moles of matter and the number of particles. So, for example, if we started with the number of moles of a substance and we wanted to work out how many atoms, molecules, or ions we had, we would simply multiply the number of moles by Avogadro's number. If, on the other hand, we started with the number of atoms, molecules, or ions and we wanted to work out how many moles we had, we would divide that number by Avogadro's number. So here's a typical problem you might get in chemistry. How many sodium atoms are in 0.234 moles of sodium? In order to answer this, we take 0.234 moles and we multiply it by Avogadro's number. And it's interesting to note the units here. 0.234 moles times 6.022 by 10 to the 23 atoms per mole. And we see that the moles cancel out, leaving us with 1.41 times 10 to the 23 atoms, a huge number of atoms. Now we can do the reverse process as well, for example, by looking at this problem here. How many moles of water, H2O, are in a sample containing 8.93 by 10 to the 24 water molecules? In this case, we take the number of molecules and divide it by Avogadro's number. So the number of moles would be equal to 8.93 times 10 to the 24 molecules divided by 6.022 by 10 to the 23 molecules per mole. The molecule terms cancel out, leaving us with a calculated value of 14.8 moles. So this definition of the mole, the amount of matter that contains as many objects as the number of atoms in exactly 12 grams of carbon-12, seems a peculiar definition for quantifying the amount of matter. In following videos, we see why we have defined the mole in such a way and how this counting unit, the mole, becomes a very useful tool in chemical calculations.